Welcome to iLecture Online, and now we're going to look at polarization. And polarization can be accomplished in several ways. One of them is by using what we call polarizers. Polarizers are devices that allow the electromagnetic radiation to transfer through only in one direction. Now, if we have, let's say, light that comes in with the electric field oscillations going vertically, and the polarizers are oriented vertically, then the light has no trouble getting through. It goes right to the polarizer unchanged. But if the electric field oscillations are at an angle relative to the polarizer, then the components perpendicular to the direction of the polarizer will get canceled out, and only the components of the electric field oscillations in the same direction as the polarizer will make it through. And you can see as the light is rotated more and more so that the electric field oscillations are perpendicular towards the orientation of the polarizer, less and less of the light will get through, and eventually, if it's completely perpendicular to the direction of the polarizer, none of the light will get through. Now, since electromagnetic radiation is typically a combination of oscillations in all the various directions, you can then see that on average, half of the light will get through and the other half of the light will not get through. Which means, if we have a polarizer that's directed like this, with the direction of the polarization vertical like that, and we have a beam incident, a beam of light which is incident, and let me use red, incident upon the polarizer, and let's say that the intensity of the beam of light that is directed towards the polarizer is I sub 0, then when it leaves the first polarizer and gets through on the other side, the intensity on the other side is only equal to half of the original intensity. And that's how polarizers work. Now, in my next examples, I have a few examples lined up. You can see how you can put a multitude of polarizers one after the other at various angles, and then you can see what the intensity looks like after it passed through a series of polarizers. So come back and take a look at the next videos, and you see how that works. Here's the next example of how to calculate the intensity of the light that passes through a set of polarizers. In this case, we have two polarizers. One that's directed vertically, up and down, and one that's directed at an angle relative to the first one. Let's say that the angle relative to the first one is an angle of 30 degrees. What will be the intensity of the light passing through the second polarizer? And of course, we can do that one step at a time. First of all, intensity 1 relative to intensity 0 can be easily found by saying intensity 1 is equal to half of the original intensity, because when light passes through the first polarizer, it loses half of its original intensity. But now, how do you figure out what happens when the light then passes through the second polarizer? Well, it turns out that the equation you use, I sub 2, is equal to I sub 1 times the cosine squared of the angle between the first and second polarizers. So let's call this theta sub 1. And plugging in the numbers, so this would be, I want to say theta I sub 1, so this is equal to I sub 1 times the cosine of 30 degrees, and that would be the cosine squared of 30 degrees. And so, there's my I sub 1, and let's see what that is equal to. So we take the cosine of 30, right here, and then we square that, and we can say that this is equal to 0.75 times I sub 1. So which means if there's a second polarizer behind the first one, and that polarizer is angled at 30 degrees relative to the first one, then you lose some additional intensity. Now, what will I sub 2 then be in terms of I sub 1, or I should say I sub 0? Then of course you say, all right, that means that I sub 2, which is equal to 0.75 times I sub 1, and since I sub 1 is 1/2 of I sub 0, we then plug in 1/2 of I sub 0, and so we can then say that I sub 2 is equal to 0, and I was going to write in percentage, but I'll do that later, so 0.375 times I sub 0. So that would be another way of writing that. We can say that I sub 2 is equal to 37.5% of the original intensity coming through the first polarizer. All right. What do you think it would be like if we now directed the second polarizer perpendicular or 90 degrees relative to the first one? So then in that case, we would have the first polarizer that would be oriented like this, the second polarizer which would be oriented like this, and so that we know that the angle theta sub 1 is now equal to 90 degrees, And I think you already know what's going to happen, because if we then plug in 90 degrees for the cosine of 90 degrees is 0, which means no intensity, no light makes it through whatsoever. So what we can then see is that if we had inbound light, which is I sub naught in intensity, then of course I sub 1, and I sub 1 would therefore be equal to 1/2 I sub 0, but then through the second one, I sub 2 would be equal to 0. No light would make it through the second one if the second polarizer was perpendicular to the first one. Matter of fact, if you have some polarized sunglasses at home, and maybe you have two pairs, if you take one glass and hold it upright, and then the second glass hold it perpendicular to the first one, you look through it, you'll see that no light gets through those sunglasses that way. So that's why polarization works so well. All right, I have a few more examples where we're going to put polarizers at various angles with each other, and more than two, and see what happens after that. And here's another example of how we work with polarizers. Now here's an interesting example. We now have three polarizers, and notice that the first one is perpendicular. The second one is at a 45-degree angle relative to the first one, and the third one is at a 45-degree angle relative to the second one, which means that the third one is perpendicular to the first one. And the first inclination is, if we look at the previous example, if we had one that was perpendicular to the first one, we'd expect that no light intensity would make it through altogether. But that's only if there's two of them, one that's vertical and the other one that is sideways, so perpendicular to the first one. But if you put three of them like that, something very interesting happens. And let's illustrate that by working out the problem. First of all, we can say that I sub 1 is equal to 1/2 I sub 0. So after light passes through the first polarizer, you have lost half of your initial intensity. Now let's look at what the intensity would be when we get through the second polarizer. Here we can say that I sub 2 is equal to I sub 1 times the cosine of theta sub 1 squared. And in this case, that is I sub 1 times the cosine squared of 45 degrees. And that's equal to I sub 1 times, and the cosine of 45 degrees is 0.707. If we square that, that's equal to 0.5, which means it's 0.5 times I sub 1. And of course, since I sub 1 is equal to half of I sub 0, that would be equal to 0.5 times 0.5 times I sub 0, which means you're now down to 0.25, or a quarter of its initial intensity. So the light coming past the second polarizer will now only be 1/4 of the original intensity. So what happens now when it passes through the third polarizer? Well, what we can say here is that I sub 3 is equal to I sub 2 times the cosine squared of the second angle. The second angle also being 45 degrees, so this is equal to I sub 2 times the cosine squared of 45 degrees. And of course, the cosine of 45 degrees is 0.707. Square that, you get 0.5. So that is equal to 0.5 times I2. And there it gives us, that's what I3 is equal to. And then, when you plug in what I2 is equal to, which is equal to a quarter of I sub 0, you see that I sub 3 is equal to 0.5 times 0.25 times I sub 0, which means that I sub 3 is equal to 0.125 times I sub 0, not 0, but 12.5% of its original intensity. This is equal to 12.5% of I sub 0. So when we put more than two polarizers, one behind each other, you can then see that the intensity of the light going to the last polarizer is not 0, but something bigger than 0, which is quite interesting. And that's how you do a problem like that.